into two sets. One is like training and another one is testing, right? So how do we use this function? We are using train test split function. So it will give four different output: X train, X test, Y train, Y test, and it should be in the same order. It should be in X train, X test, Y train, Y test. Otherwise, it will be the order will be changed, and you can't use it for the analysis. While you will get like lots and lots of errors. And what are the inputs for this train test split? First is the X data. We know what is X, and we know what is Y also. So here it is asking what should be the test size. So what is the minimum test size I said? What should be the percentage of the data that can be used for testing? Anyone? It is 20 to 40%. Here I'm using 30%. That's why I said 0.3. So in this data set, 70% of the data will be training, 30% of the data will be test. So if I have 20 samples, how many samples will be testing? How many samples will go for training set? I have 20 samples. If I split by 70 is to 30, what is my training sample number and testing sample number? Just put your answers in chat. No one? It'll be if it is 20%, like 20 sample means around 6 will be into the test set, others will be train set, right? Right. And random state is something like where we say to get when you do like multiple iterations, right? Again and again, if you're running, you might get different results. So to avoid that kind of confusion, we put some seed. That's what the random state is to uh, for the better reproducibility, we are defining some random state. I'm just giving it as one. You can give any number you want. Okay. So you can see here, right? I have a X of 10 samples and the X train is 7 and X test is 3. If I change the test size to 0.2, then it will be 8, 8 training sample and 2 test sample. Okay. Everyone gets it how we are creating a training testing split? Because these are all the important points. How you are getting a data, how you are pre-processing it, how you define the training set, how do you define the testing set. Now we have the training set, testing set, like we did the last one. I'm defining linear regression to a variable and I'm fitting it using X of train, Y of train, Y underscore train. I'm fitting the model for this data and I'm trying to predict it. So while in predict is the values predicted for the 3 data points we have. So we can see what it has predicted. This is what it's predicted. Now we have to see whether it is predicting good or bad, right? So I'm asking, so dot score will tell you the R square value. So whenever we draw a graph, we will see the R square, right? If R square is like closer to 1, that means the model is like trying to fit every data and it's like good model. And if the R square is less, that means like it cannot account for most of the data. So it's better not to use that model. So for this data, the R square value is 0.25. Is it good? Can we stop here? Anyone? What's your thought on this? Is this model good? Because we are getting around like 0.25. Is this good? It's not, right? It is not good. Because the value should be closer to 1. Why it is not good? We will see how we can do it in residual plot. We can draw a residual plots using yellow brick dot regressor. These things, for residual plot, I'll give you the codes. Like I'll forward you anyways. Like I'll share this collab notebook with you. But you should know how we are plotting the residual plot. So the input function for the input for the residual plot is whatever model we have built. And again, we are trying to fit the same using a training set and score it using a test set. This is how our residual plot looks like. If you see here, it's not like scattered around 0. It has some structure. It looks like an inverted C, right? Just like the quadratic function. It's something like this, right? So what we think, it's not a this data cannot be explained by a linear regression. Maybe we can go for the polynomial regression model. That's why we are going. So we'll start with degree 2. So polynomial regression with degree 2, we call that as a quadratic. It can go to degree 3, degree 4, whatever degree you want, right? So how can we do the polynomial regression? It's exactly the same as linear regression. If you know how to do that, it's the same everywhere. First, you have to define a model and label a variable with that model, fit it using a training set, predict it using a test set, evaluate a model. This is the 4 steps which we will be repeating for most of the machine learning models we will be learning, right? Like I already mentioned, we are defining model to a specific variable. Here I'm defining second degree polynomial features to variable poly. And next is to fit this data. Okay, before fitting in polynomial features, right? We will be using a linear regression only. But what we are doing is like instead of changing the model, we are changing the data. That's what that's why I mentioned fit transform. So transform the X train to X train 2. So it will try to predict, like get the X of polynomial features degree 2. What is degree 2? It will be like ax square plus bx plus c is equal to y, right? So it will try to predict the X of it. Okay. And X test 2 will also be the same. So if we see X train, sorry, print X train. I'll just print the first pi. Print X test. It is throwing me error before that. Okay, I haven't even. Run the polynomial feature. That's why. See, right? Okay. This is the X train. Like first, okay, it should not the first. Since we have only 3 test set, we have like 3 data points only. For the training, we are having 5 data points. Now we will see how the same differs for the fitted values. This is the untransformed. X train is untransformed one. X train 2 is transformed one. You can see how it has been changed, right? This gives A, B, and C. This comes from where? Ax square plus bx plus c. Okay, that is how it calculated this 3 cross, sorry, not 3 cross 3. It's 3 matrix, 3 column matrix. Okay. So now we have the transformed data transformed to fit the polynomial function. Now we will do the same steps. We will try to assign the model to specific variable polyCF and fit it using a training set. Here, remember, we are not training it using untransformed data. We are training it only with the transformed data. Okay. Fitting the model, then predicting the model using test set. Okay. Now I have predicted the Y. Then we will look for the evaluate the model. How we will evaluate? Look for R square or mean squared error. So here I'm predicting the R square error. It can be done by model.score the value, the X test set and what is the Y test set. Here you can see 0.9549. You can see what is the linear regression also. It was around 0.25, right? Where it is. See, it's 0.25. But when we changed it to quadratic, it changed to 0.95. Do you understand how important it is to select a proper model? We can say both are working. It doesn't show any error. But still you can see how much improvement has been made when we use the correct model, right? We are able to predict 95% of the data good. So these are all important when we apply it in the real cases. So in case if you are building a model to predict whether the person is having a cancer or not. Okay. So if you say like, okay, I will say 25% of the time, I'll whatever I'm predicting, if the person has a cancer, if I'm saying yes, then it is true. Only 25% of the time. 10 பேர்ல 4 பேருக்கு தான் நான் சொல்றது கரெக்டா இருக்கும். 10 பேர்ல லைக் 4 பேர்ல இப்ப நான் 4 பேருக்கு 2 கேன்சர் 2 இதுன்னு சொல்லியிருந்தேன்னா அது உங்களுக்கு மட்டும் தான் கரெக்டா இருக்கும் அப்படின்ட்டு சொன்னோம் அப்படின்னா இட்ஸ் நாட் அ குட் மாடல், ரைட்? வி ஆர் ரிஸ்கிங் அதர் 6 திங்ஸ். பட் உங்களால வந்துட்டு இப்ப 10 பேர்ல ஐ கேன் சே ஃபார் 9 people whether it is true or false, then it is like a good model. In that cases, it's really important to build a appropriate model for the specific application. Anyone has any other questions? Okay. We'll move on to the next part. As I mentioned, like here we are just looking at what are the different metrics. We already saw R square and MSE. MSE, we are just like identifying it using mean squared error. And R square, you have the R square function also, or if you are giving like model.score, then also it will show the R square value. So this is what the comparison is. When I use a linear function, the R square value is 0.257, but when I move to quadratic, it is 0.955, which is like a drastic increase. And even in the MSE should be low. If the model is good, then the MSE should be low. So if you see here, linear has like 2600, whereas quadratic has only 158. Now we can say, yeah, this is good model. And we can check it with the residual plot also. So when we check the residual plot for the linear regression model, that means polynomial model, you can see the dots are scattered here and there. It's not like the previous one, which is like in some inverted C shape. Right. Okay. This is just again the visualization method, how the linear regression fit and how the CLF model, like the quadratic function model we created fit. So what I'm doing is like just plotting the X train and Y train and trying to plot a line with X train and the model predicted Y train. Okay, the first one is whatever we have, our own data, the actual data. And the second one is X-train with the model predicted data. That is what the line represents. This is a linear regression. And you can see there are like lot of residuals in this. But when I use the CLF model, I have predicted the red dots are predicted values. Okay, CLF predicted values. And if you see here, it's nearly follows the same path as the data. Does anyone have any questions? If not, we can go on to regularization. Okay, move on to regularization. So we have seen linear regression, polynomial regression, where to use it, when to use it. We saw all of this. But when we use these models, we should be careful, right? There might be a chance for underfitting a model or overfitting a model. Okay, what is underfitting or overfitting, right? So I have a data something like this. The red arrows like crosses are the actual data. And you can clearly see that if I fit a linear regression, it can't predict all of the points, right? It is missing out so many data points. So this is what we call that as underfitting. Or if I try to make it like more lenient and try to explain every point, then what it will do is like when we have some new point, right? It can't predict properly. The testing will be very less. Testing data, like testing accuracy will be very less. This is what we call that as overfitting. So if the training accuracy is high and test accuracy is very low, that means you have overfitted the model. So we don't want underfitting. We don't want any overfitting. We wanted the fitted model. It should be just able to explain the data, but not very extensively explain each and every data. Okay? This is what we are going for. So how can we get this? To avoid this overfitting, we can take like few of the steps. One is we can reduce the number of features. So if you see here, while doing underfitting, we took only one feature. But when we do overfitting, we have lot of different features, 1, 2, 3, 4, right? If we reduce the features, then the overfitting will also get reduced. Okay. Second way is to do the regularization. So the regularization can happen in two ways. One is we will keep all the features. So if we are taking 4 features, then we will keep all of those x's, but we will reduce this theta 1. I'll reduce this theta 4 to 0.0001. That is essentially a 0, right? And I'll also reduce this theta 3 to 0.00002. That is also again very less than 0, like equal to 0, kind of. So we can omit these two. This way we can reduce the overfitting. Okay, this is what a regularization method is. So this is what I mentioned. So this is how the data looks like. And the green line is enough to explain the data. This green line is enough to explain the data, but when you have multiple variables, you will get this blue line, which is like so jiggly. And also, if you have new test set, you can't predict it, right? We want this also. We don't want this underfitting. We don't want this overfitting. We want something where we have low bias and low variance. Okay. And we have two different regularization method. One is ridge, one is lasso. Ridge expression is where we try to say all the coefficients should be similar, right? So we have seen four different parameters, theta 1, theta 2, theta 3, theta 4. I'm saying theta 1, theta 2, theta 3, theta 4 should be nearly equal. If like theta 1 is 0.12, theta 2 should be 0.3 or 0.4. Okay, that is what the ridge regularization is. Lasso means I'll say I'll take only theta 1 and theta 2 be higher. Theta 3, theta 4 should be 0. That's what I explained earlier, right? Theta 3 will be like some 0.00004 or theta 4 will be 0.00002, something like that. Okay. And lasso can be used if you want to do any feature extraction. So for few of the studies and all, you might have lots of features. Like even I have seen models with 1,000 features, but you can't explain a output using 1,000 features. In that case, you want to do the feature reduction and feature extraction. From 1,000 features, you want to bring down to 10 or 15 features, right? That's when we will do the lasso. And if you want to predict the impact of that predictors, like the features on the response, then we will be using ridge regularization. Okay. Anyone have any doubts in regularization part? If you don't have, we will move on to how to do this regularization uh, in uh, Google Colab, right? For a ridge or lasso, we will be importing the specific function called ridge. So this is from the sklearn.linear model. So from that, I'm importing the ridge. Again, it's same like the previous models, whatever we have created, right? We will be assigning the ridge to like the ridge model to the variable, and we will fit it using train and test it using a ridge.predict. Okay, we'll fit the model and then predict the model. I have done this for both linear regression and the polynomial regression. We can see how the linear regression model has been showed and how this model is shown. So if you see here, you can see the ridge regularized linear regression model is like, again, it's something 0.26 and it has only one variable. That's why it is called linear regression. And when I have two features, it is 0.96, right? Lasso also nearly the same. We will be importing lasso from sklearn.linear model. And here I'm assigning the model to variable and fitting it for training and predicting it using a testing model. And I'm checking what is the training score and testing score so that I will know whether this model is good or not. So if you see here, the training is 0.95, testing is 0.26, and the number of feature used is like only one. And with this itself, you can say this is not a good model. Why? Can you explain why? Even though we tried avoiding the overfitting, it still has some overfitting because training score is very high than the testing score, right? So you may have to tune in a bit. How you can tune it? You can use these hyperparameters. Hyperparameters are nothing but the values which are given to the model. So if you see for lasso, we are already giving some value called alpha, right? If you tune something like this, then you might get a better model with good training accuracy and test accuracy. Everyone is clear with this? Anyone has any doubt? Okay, thank you, Sandhya. Okay, until now we saw how we can do it with the uh, data we created. Now we will use the data, real life data. So if you want to know about the data set, this is a house pricing data set. So there will be like few parameters which will predict the price of the house. And we want to build a model. So if people in real estate will try to predict the land price, right? Using few of the parameters like how close the bus stand is, how close the railway station is, how close the other schools and other things are, like that. We will use different parameters to predict the price of a data set is about. First, what I'm doing, I'm importing the data set. So Python sklearn does have a lot of data sets within the package itself. So I'm using that data set, which is present inside the sklearn. So I'm downloading it from sklearn.datasets, and we are using load Boston, like Boston dataset. That's why I said load Boston. And okay, I'll just put all of this in here. We can see how the Boston looks like. And this is how the data looks like. It's so unorganized and we can't even see what is what, right? So in order to like see it clearly, you already saw about the pandas. So pandas is something which helps us to which helps us to uh, visualize the data in data frame, right? So I'm changing this data, whatever I have, to the data frame. How we can change that? I'm just giving pd.data frame where change the Boston.data using feature names. Feature names are already present in here, right? So using this as a column names, create a data frame, right? So how the data frame will look like, we'll see. Now you can at least see what is what, right? You can see there is a column called Krim, there is Zayan, there is Shas, Nas, age, distance, radius, tax value, and all those different things you can see, right? Now, these are the, if you see in this thing, you can't even see any price, right? This is because this only has X, that means only the features, right? So the Y value will be present in Boston.target. Any data.target will have the Y value. Now what I'm doing, I'm just like defining a column called price. This is how you can create a column. Our data frame, square bracket. Within that, you will be giving your column name in quotes, then equal to Boston.target. I'm just looking at the first 5 rows. That's why I used what Boston df.head. So the head will give you only the first 5 rows of the specific data frame. So now you can see price is the Y. Okay. Now what is X? What is Y? The first column, like the column still L stat is X, whereas price is Y. That's what I'm defining it here. I'm saying X is nothing but if you drop the price value, then you will get the X. And only if you take the price value, then you can get the Y, right? I'm also looking at it again. When you say see the X, you shouldn't get any price value. This is the shape of our X. So we have 13 different features. That's why we get like 506, 13. 506 is a different sample. So like we have 0, 1, 2, 3, 4, right? It will go till 506. And you can also look at how the data looks like using a like data frame dot describe. I hope like these are all you did it in the visualization class and you might remember it. I'm just like refreshing it, because whenever you start a analysis, right, whenever you take the data, you have to do all these things. You should separate the features from targets and look at different types of analysis to check whether there are any NA values or there are any correlated values. You have to do all this pre-processing before getting into the machine learning. That is why we are looking at into each and every step. Even when we go for like other logistic regression or classification, we will be doing the pre-processing and we will be doing initial steps for the data before getting into the model. Okay. I guess like you have some session at 6, so maybe we can stop here. So for a quick recap, what we saw is like we saw what is linear regression again, and why, like what is the polynomial regression and what places we can use a polynomial regression, and what are the different metrics like R square and RMSE, mean squared error, for a evaluation of a model. And also we saw few of the methods how we can pre-process the data. We will look at remaining pre-processing and how to fit the models to linear regression and polynomial regression tomorrow. Okay. Do you have any question? If you didn't understand, please let me know. Otherwise, it will be very difficult moving forward. Just remember these 4 steps. Whenever you get a data, first pre-process it. Pre-process till you get a good data, then split your data into X and